and today I'm going to be presenting my project, Qubit Allocation, as a combination of the Subgraph Isomorphism and token swapping algorithms by partitioning with a failure heuristic. So first, as an introduction, the Qubit Allocation problem is for quantum circuits on actual quantum architecture. Quantum circuits are usually arbitrarily designed, meaning that any logical qubit can interact with any other logical qubit. However, the reality is quantum architecture is not that flexible. Physical qubits on the architecture have only certain neighbors that they can access. Having this type of restriction means that the logical relations in the quantum circuit cannot actually be run on the hardware. So instead, the qubit allocation or qubit mapping problem is essentially solving that by transforming and moving the locations of the logical qubits in the physical architecture through swap gates in order that the whole entire circuit can run. And most importantly, usually the approaches try to optimize some type of factor such as time, depth, or number of gates. My approach is using subgraph isomorphism and token swapping, basically trying to optimize for the largest number of sublists or longest number of gates that you can use a mapping through subgraph isomorphism. And if it fails, you use a failure heuristic to basically narrow down the gates. So this is basically the overview. The quantum circuit file and the coupling graph file are the inputs to the qubit mapping problem. And the compiler will basically just go through these steps. First, it'll pre-process the circuit, which is basically just parsing through the gates into basically a list of gates, and also live ranges. And live ranges here are defined as the control relations, basically gates that interface with two logical qubits. Basically, it's just a list of those gates for every pair of qubits, and it's an easy way to access them. And G basically means you're building a coupling graph from the coupling graph file. And what you want to produce is a series of mappings for the whole entire circuit. And after you find those mappings, you want to calculate the swaps. That's the token swapping part. And finally, for the compiled circuit, you basically you take your mappings, you take your swaps, and you go through all the gates and replace everything that you had before. And finally, you output the circuit, which is what we want. So SIPF, which is subgraph isomorphism partitioning using a failure heuristic, is basically the framework for the qubit allocation. This is where the actual mappings are made, and essentially this is a partitioning algorithm. So it starts off with the left and right indexes covering the whole entire circuit, and it will make a bunch of islands. That's what I call them. Basically, they're logical graphs between logical qubits in the circuit. And the reason there are islands is because of benchmark programs, which basically randomly generate circuits and gates. So it makes it very hard. But I think in most real world programs, all the qubits interact with each other at least once if they're meaningfully used. So all these islands in the logical relations have to be mapped for a mapping in a certain range. And this basically happens through backtracking, right? Once you build the islands, then you use backtracking for one island at a time, starting with the largest island to the smallest island of 1, which can usually just be plugged in at any undefined qubit location. And if a mapping is found, then you add that mapping and you update the bound. So the lower bound is now the upper bound, which you didn't include before, and the upper bound is now the maximum amount of circuits. And this loop basically continues until all the gates have been mapped, which means L is actually equal to the number of gates in the circuit. On the off chance that the failure heuristic fails, it will just decrement the upper bound by 1, so there won't be anything stuck or segmentation faulted. Otherwise, it will find the latest gate of the earliest conflict qubits. So essentially, given all the conflict qubits, right, they all have certain number of gates within the range, the lower and upper bound. You want to start at the latest qubits of all the conflict qubits. Backtrack level. So this is basically how you recursively search it, and there's basically 2 levels to this. First, there's recursively searching for islands, right? If there are multiple islands, backtrack level handles it at an island level. So if the island only has one logical qubit, then it'll basically map it in this recursive function. But if not, it'll have to basically do some searching similar to the DAF algorithm mentioned in a paper in Sigma 2019. And this will build a directed acyclic graph for the island and a bunch of candidate sets and edges, as well as the candidate space. And this logical graph DAG will basically be matched upon this candidate space. And it's basically just recursively, exhaustively searching through until it finds a mapping. Or if it doesn't, then it'll just return false, and this means that it can try something else. All in the meantime, if the logical island is not just one, then you have to use the backtrack level helper. And this is basically a simple depth first search. And basically it'll just try out like mappings for candidate physical qubits for each logical qubit that's in the frontier. And if it works, then it'll return true, and it returns things by setting the inputs to basically the modified scene mapped and mapping. And otherwise, it'll just update the failure heuristic and try something else. And if everything fails, it'll return false. So the failure heuristic was one innovation that really drove and inspired this project. Essentially, while you're exhaustively searching through everything, you basically want to look at options where you want to search for options with the largest size. Because even if it's a partial mapping, if you know the size and you know what qubits cause the conflict, then you can actually use that as basically some information from failing to find the next upper bound. So if it fails, it'll check the current maximum size in the failure heuristic, and if it's less than it, then it'll just ignore it because that means the current failing partial mapping is worse. If it's equal, then it'll just add the conflicting qubits, and if it's greater than, then it'll actually just completely clear out all the conflicting qubits that were matched in the failure heuristic and only add the current conflicting qubits and update the new maximum size for the heuristic. But there's some cases, I'm not sure why, when the conflicting qubit gates are actually just empty. And in that case, it'll just default to decreasing by 1. But in most cases, it should just be finding a gate within a certain range. So calculate swaps is the token swapping part of this. There are a lot of things that you could do, but I went with a very simple depth first search heuristic algorithm. And more importantly is that it's bounded. So since it's bounded, it basically means you're guaranteed a minimal thing if your bound is proven to be optimal. And due to a paper written by Miltsau in 2016, given the minimal distance from each logical qubit position to the next logical qubit position between mappings, uh, if you find all, if you sum up all the distances added together as an overestimation, the lower bound is actually that distance divided by 2. So the sum of all those distances divided by 2 is the lower bound. Since for each swap, the best you can do is actually move, if you swap 2 qubit locations, the best case is that you move both of them towards the shortest path, which means if you keep doing that on average, it'll actually, on the optimal path, uh, the cost will be divided by 2. Uh, so yeah, the algorithm is very simple. First, it creates a distance matrix. This is basically like dynamic programming. It uses the Floyd-Warshall, and it finds all shortest paths for all pairs of physical qubits. And that is basically used for the recursive depth-first search, and it's bounded by depth. And it'll start from the cost divided by 2, right? All the sum of the distances divided by 2, and it'll just try to find a series of swaps. And once it's found, then it'll just add the series of swaps to the total list of swaps for all the pairs of mappings. But if it doesn't, then it'll just try to go one level deeper. So you always start with the minimally proven number of swaps, possible swaps, if it manages to find the optimal one. Otherwise, it'll just keep on increasing. So this is basically the architecture. As you can see, there are the 2 inputs there, and it'll go through the pre-processing, which I will talk about very soon. Then it'll go through the SIPF, which will find all the mappings. And once you find all the mappings, you calculate the swaps and use those to compile the circuit. So this is more implementation based. The circuit parsing, I used a custom parser that just literally went line by line and parsed it out. And this is because if you use the chasm parser provided, it actually parallelizes it for you and produces layers, which is not good because if you insert swap gates into there, it'll actually produce an incorrect thing, because the only reason they were able to parallelize it into layers was because they already knew that the circuit was correct. The way that the gates are actually ordered in the C++ program, there's no guarantee. We already went over the qubit mapping and token swapping. So the compilation, this is just some metadata. We'll produce the number of swaps and mappings, which is basically we can just get directly from what we've been doing before. But the depth and number of gates is actually done by using the compiled circuit, right? Once we replace all the new physical qubits based on the mapping, I ran it to a temporary file and passed that into the parser, which we couldn't use before, but now we can. And it'll actually parallelize and do everything for us. So it'll give us the number of gates and the depth, which can be used to compare against the benchmarks. So I used the feedback circuits given in lab 1 basically as the benchmarks, and I used it across all these combinations, all these across the different architectures except for the Queco ones, since they're built only for Aspen 4. Since they have 16 qubits, it's the only one that'll work anyway. And I compared it against Soraichi et al.'s 2019 and Uppsala's Enfield reference compiler for their BMT algorithm, which is basically the first algorithm which proposed a qubit allocation as a combination of subgraph isomorphism and token swapping. So they had 5 variations that I could find in their compiler, and for mine I have 2. The default one is the one I've been showing you, and the optimal one is instead of using the failure heuristic, each time it fails, you always decrease the upper bound by 1. So it'll always get the maximal isomorphic sublist. And the Enfield compiler, I didn't really change any settings. I just rewrote these architectures into their JSON format and use it in their field. And on average, the SIPF algorithms always did better than the end field, which is really great. But there was some cases in terms of time uh, in which the end field and SIPF algorithms differ. And this is because the end field algorithm, time and complexity, scales with the number of logical qubits. Since it's doing basically an exhaustive search with some bounds, the more qubits you have, the more it has to search for the mappings. On the other hand, the SIPF, it doesn't have to incrementally search through all these things in a tree. It basically generalizes a whole series of gates as just one graph. So it could be 3,000 like gates, but it could be just reduced to the number of logical qubits that you're using, which is really great. But however, it does perform poorly if the circuit does have a lot of uh, basically conflicts with the physical architecture. So the more mappings and more swappings you have, the more time it takes, especially for token swapping, since we're using that very naive searching algorithm. It can really become a bottleneck. And the SIPF optimal algorithm, which is the one that decreases one at a time, surprisingly does better, obviously because it's optimal, but it is also faster. And I think this is because the default failure heuristic algorithm, it produces more mappings on average, and every time you add an additional mapping, it's another token swapping calculation you have to do, which is really expensive relatively compared to the SIPF algorithm. So in conclusion, basically the SIPF algorithm uh, works pretty well considering that it's not very complete. Uh, and it's not very complete because as compared to the BMT, it doesn't consider every single uh, possible mapping for a certain gate range. Basically, once it finds a mapping, it only considers that one and moves on to find the next one, even though there might be a more optimal combination of consecutive mappings, like the BMT does. But even the BMT only really considers it between two mappings. Further work could probably be done so that the whole entire circuit could be searched through. And I think with SIPF, since you're optimizing for maximizing the uh, you're optimizing for the maximum like sub-circuits basically, the amount of searching you have to do through the circuit will hopefully be less, and it might actually be possible to actually do that type of search. The FL algorithms, they're really good, but on average the SIPF just perform much better in both depth and gate and time, except for the cases which I mentioned earlier. And yeah, that is my project. I also have a bunch of benchmarks here, and you can see them. I measured the real time, the user and system time, which is basically the CPU clock time in milliseconds, and the depth and the gates, which are from using the Chasm parser. And this is also compared to the Enfield one. And the Enfield one has its own stats option, which basically prints out depths and gates. The real time and user and system time, I was using the bash shell time command. Yeah, thank you for listening.